Welcome to solverfy.
This is the answer to Chapter 19, problem number 43 from the Smith Organic Chemistry textbook. And this problem has two parts. In part one, we're asked to explain why paranitrophenol it has a lower pKa and is therefore a stronger acid than phenol. And in part B, we're asked to compare paranitrophenol and metanitrophenol. And so basically, to answer part A, I'm going to draw out all of the resonance structures for paranitrophenol, and we'll actually reuse that for part B as well. So here I've drawn a deprotonated paranitrophenol, and so the very first resonance structure that we can draw would come from here. That's all right. So it would come from here. The electrons of this double bond would revert to that carbon. And so our first resonance structure is going to look like this. And the lone pair and the negative charge are now on this carbon. And so basically, we're just going to draw resonance structures that move this lone pair around the ring, and eventually it'll end up on the nitro charge. So the next potential resonance structure looks like this, or the electrons would move like this to get us there. And so I'm actually going to draw out the structure of the NO2 group because it will make, we'll need it drawn all the way out. And so right now, the lone pair is on this carbon, so there's a negative charge there. And then one of the oxygens of the nitro group has two bonds and two lone pairs and no charge. And the other oxygen of the nitro group has three lone pairs and a negative charge. And the nitrogen of the nitro group has no lone pairs and four bonds. And so it is going to have a positive charge on it. That's the way we always represent a nitro group. So from here, this lone pair can add in here, and this double bond to this oxygen can break. And so we get to this resonance structure, which is really the key resonance structure here. This is by far the most important one. And that is because in this resonance structure, the negative charge that started on the oxygen that we deprotonated can be delocalized onto this other oxygen of the nitro group. So we still have a positive charge on our nitrogen in the nitro group, and then each of these oxygens has three lone pairs and therefore a negative charge. But that's good. It's certainly better than the lone pair and the negative charge being seated on a carbon in the ring. This is much more stable. Remember, charges should be seated on electronegative atoms whenever possible. And so, so this is a much better resonance structure, or a strong resonance structure, where you could say, It's we could call it a good resonance structure. And again, that's because the negative charge is seated on an oxygen, which is electronegative. Good resonance. Oh, lag is killing me. Good resonance structure. Okay. And so this is important because obviously in phenol, there's no nitro group. And so phenol doesn't have access to this type of resonance structure. So I'm omitting the rest of the resonance structures here, but we can delocalize the negative charge, the lone pair, back into other positions around the ring. And so there are a couple other resonance structures, but phenol has access to those resonance structures as well. So this is a very strong resonance structure that is unique to paranitrophenol, at least when we're comparing paranitrophenol and just regular phenol. And so since this very good resonance structure exists, it helps to stabilize the conjugate base. And we should remember that the more stable a conjugate base, the stronger the acid. So this is the explanation for why paranitrophenol has a lower pKa than does just phenol. So then here on the second page, I'm going to address part B. And part B is asking us to make a comparison between paranitrophenol and metanitrophenol. And so I've just drawn several resonance structures, at least all the important ones for paranitrophenol. So now I'm just going to draw some resonance structures for metanitrophenol, and hopefully it will become clear from doing that why the meta has a higher pKa. And basically it's because meta nitrophenol does not have access to that resonance structure. There is no resonance structure for metanitrophenol where we can seat the negative charge on the nitro group. Okay, so this is deprotonated metanitrophenol. Oof. I apologize. I'm not sure why my computer's struggling so much to draw this evening. Okay, so here would be the deprotonated metanitrophenol. And so just as we did for the paranitrophenol, we can begin by moving electrons like this. Okay. And all right. So we begin moving electrons like that. So here is our first resonance structure. Oh my goodness. This lag is brutal. Okay, so oh my God. Okay, so here's our first resonance structure. The lone pair and the negative charge are on this carbon. And so from here, we'll proceed exactly like we did in part A. So the electrons can move like this. Okay, and so now our negative charge and our lone pair are on this carbon. And from part A, which I'll take a look at again real fast, in part A, that's the carbon that the nitro group was attached to. And so that allowed the electrons to then move down towards the nitro group. But in this meta nitrophenol, that's not where the nitro group is located. And so what actually would happen is the lone pair of electrons would go here, and this double bond will break, and the electrons will revert to that carbon. And so essentially what's happened is the lone pair skips over the carbon where the nitro group attaches to the ring. And so those electrons don't have the opportunity to delocalize onto that nitro group. And so since they can't delocalize onto that nitro group, we don't really get the benefit of the electron withdrawing nature of that group, the way that we would in paranitrophenol. So we have double bond here, the NO2 here, and then as I said, the lone pair has sort of skipped over the carbon that we would need it to be seated on to then, as its next move, delocalize down to the nitro group. And so we don't get the super stabilizing effect of the presence of the nitro group that we see in paranitrophenol. And so that's why metanitrophenol is not as strong of an acid as paranitrophenol. And so this is the answer to chapter 19, problem number 43.